Like the speakers that I did not introduce in the morning, I don't think he also needs introduction. As Professor Raj Reddy mentioned, doesn't Pining work in computer vision, machine learning, etc. So I'll let Professor Jawahar take the stage. Thank you, sir.
Thank you for the opportunity. So I'll try to give a quick overview of what is happening in the computer vision area in recent past, and hinting at the major threads in this space. However, when I tried to summarize this, I found that it is not very easy to compile or put together the major themes in this space, so I might have missed a lot of things that are happening, but let me give an attempt. So computer vision as a task, like as an image understanding task, has been evolving over many years, decades, and the focus has been on understanding the content of it in terms of what is the scene, what are the objects present there, where are the objects present there, how are they placed, who is close to what, a set of questions that you can infer out of it. So this has been the broad focus of computer vision for many years, or at least a dream of computer vision researchers and practitioners for many years. So now, to give you the background of how this community has evolved, the concern has always, like, given an image, how do I interpret? What is in it? How do I know whether my understanding of the image is good, whether my processing results of the image is good, so that we are happy with the success or failures of that algorithm. At least we know whether it's succeeding or not. So I'll take a history lesson from the low-level vision or mid-level vision, where anybody who has ever tried to understand or process image, one of the first thing that we all learn to do is to detect edges. Detect with the Sobel operators or the small, tiny mass that we all learn to write programs to detect edges. How? If you look at an image like this, a natural image like this, where if you want to detect an edge or a contour or on a separate an object, the task is very difficult. And very often very subjective. So one of the first attempts in this space has been to understand this subjectivity by the help of multiple human experts saying what is an object, what's an edge, what's a contour. And then using this as a benchmark, try to see how algorithms perform and how to characterize the algorithm with a performance metric which we can compare and see the progress over years. And we see that over years we had approached closer and closer to human limits of understanding the object contour. And we are now reasonably good at processing some of these tasks. But the modern computer vision centers mostly on higher level tasks. So in general, this sort of an attempt gives us few lessons. One, we need a formal definition of the task and a realistic data set with annotation on which we can evaluate the performance, a measure that can quantify the performance, basically. Algorithms that can use this annotated data. And on top of it, how a community can use this data and see the progress over years. So this has been the primary driving force behind the computer vision research in the last couple of decades, but seriously. So in the higher level task, where the task is usually not just detecting the extent of the objects or where they are present or understanding the properties of the pixels or regions, it has been mostly recognition. Early attempts on recognition was on objects which have a lot of presence in natural images like humans, human faces, text, characters, character recognitions, and vehicles and understanding their poses or positions in natural images. So the history of the modern computer vision, or at least which became very hot in post 2000, where the task of understanding were formally casted on wide variety of natural images. Internet repositories of images became very popular. We all had our own cameras, and we all had captured, and we found that the applications of computer vision will have to be on natural data captured in the wild conditions. So in this stage, the community started building data sets and task definitions. So the initial attempt of object recognition was capture images of the objects, maybe in a focused manner. And then when it came to Pascal and ImageNet, the late 2005 and onwards, we were capturing images or processing images which were more and more wild and naturally captured in the natural settings. And the task became more and more formally defined. Initially, the task was to say, what is this object? Then it became like, tell me where is this object in this image? And how is it placed? Third level, we went to the level of, tell me which pixels are on this image itself. So the task became, even if it's a bike, which bike it is. The fine-grained understanding of the visual content in terms of the pixels were all, in terms of the properties, like which bike or which make of is it. This level of task got formally categorized, formally stated, and the appropriate data sets for this task came into the literature. And this was the major phase where the formal definitions and improvements in the community was measured. The Pascal, for example, which started in 2005, by 2012, they found that, okay, this task will have to move forward with a new set of tasks. Interestingly, at the same time, the natural data set collected with the ImageNet, one of the largest data sets available of images, which had extremely large number of categories of images and a number of examples, became also one of the very important player in the emergence of the deep learning. Because the turning point in this history has been this AlexNet, which appeared in 2012, where the task on image, the classification, the performance of the previous era, like the last 5 years, we have been inching by like improvements by 1%, 0.5% over years. While in 2012, a completely different approach, which is an end-to-end training of a deep neural network, gave a significant improvement of close to 10%. This attracted the researchers, and this made this convinced the larger, wider community that deep learning is robust, and this is usable for a variety of tasks, and people can get into this, and the rest is possibly the still modern computer vision. So this, sorry. If you look at the historical development, the Swift and the previous era, previous to deep learning era, the performance was 25. And from 2012 onwards, like very fast, we came down in the error rates and became quite comparable to the human error rates in, say, 3-4 years' time. A number of deeper and deeper architectures came with better and better learning algorithms, better and better methods to design architectures which are more compact, efficient, and made this is where the post deep learning era, the architectures moved. Now from a pure computer vision point of view, there are a lot of other concerns in terms of what do we mean by understanding images and how do we represent images. The features or the representation of the image has been very fundamental issue in the image understanding or image analysis space. So we would like to have features or representations which are superior, and the previous era, previous to deep learning, we have been doing mostly histogram-based features, borrowing ideas from bag of words and a number of variations of it which connects to the IR community, the signal processing community. Now, since the image classification problem is solved for a specific ImageNet task, we ask the natural question that, okay, look, what does it mean to the larger computer vision space? So the answer is, the features that we compute by training the ImageNet are generic. This gave us a new hope that a network which is trained to do a certain task in the image space is fully useful for a number of other tasks. You train the neural network or the deep learning algorithm for a certain task. However, in the entire process, you build a set of representations which are widely useful for a wide variety of other computer vision tasks. So you have a neural network here which was trained on the specific task of classification. However, if you chop at some layer and make a representation that is useful for recognizing a new object or a new class or a new type of visual data. Now you can reuse this, and you can also refine these features. You can improve these features with the help of transfer learning, or you can adapt the knowledge that is trained in one domain or one category of images or one type of images to a new type with relative ease. And people, in fact, have looked into how generic or critical is this, the amount of data into the first domain. It was found that with a small amount of pre-training itself, you can build solutions which can be very useful for a new task. So in this case, a deep neural network which was trained on a ImageNet is completely extendable to a new task of scene classification, which is completely a new set of images, new task definition itself. And naturally, the concern of, or the positive result of seeing generic features also resulted in curiosity of what these neural networks learn, and found that the learned concepts are this result. So if you try to open the deep neural network and look at what neural network learns over these layers, it was interesting to see that the initial layers of these neural networks were learning features which are very generic, like small edges or corners, and the later layers were learning semantically richer concepts like objects or object parts, and this gave us explanation about how these features are generic and how do you transfer these features from one space to the another space. Then came the question that, okay, look, we have been seeing only the success of supervised learning. Can we do something beyond that? Creating annotated data for various tasks is tedious, and how do we avoid it? So the vision community had the answer to this was use the larger context and learn in this way so that later on, or the features that you learn in this process is useful for other tasks. To give an example, if you have an image and you want to guess, you chop or you mask a certain region of the image and say what it will be. So similar to the ideas from Word2Vec, where you are given a sentence and remove a word and ask you to predict the word given the context. Similarly, given the rest of the image, can you predict what could be there in this patch? And if you are able to do this task, then the features that you are learning is also generic. So this sort of ideas of learning from surrounding text, learning from previous frames, learning from parallel data. For example, in the case of Wikipedia pages, like Wikipedia images and text, so the text topic models can act as learning signal or supervisory signal to the image classification task. And so this entire class of algorithms which does not really use the fully supervised learning, which use in a way unsupervised or self-supervised learning, or learning from itself by harvesting the supervisory signal within it, became very popular. Now, we had seen the features that are useful for machines for processing. Now, what about humans? If you want to have representations that are more useful, one way to look at this is building representations which are human understandable and human should be able to manipulate. So this was attempted with the help of, by connecting to language, and in this era there is a lot of connection between vision and language surfaced. So instead of understanding the image as a classification, the newer tasks like captioning, given an image, can you write a sentence about it? Or given an image, can you write a number of phrases corresponding to what this cat is doing in this image? Or the relationship between objects, like cat sits on something. Or this, so this level of phrases or the connections surfaced. So in general, all this looked at a set of supervised methods where you have an image and a set of sentences, and you would like to learn the relationship between them and learn models so that you can generate a number of a caption or a human understandable description by composing the understanding of the objects and their relationships. So these are a few more examples where we are able to generate human-like captions for the corresponding images. So here you can see a number of such the compositional descriptions appearing here, where objects and their surroundings are connected together to come up with phrases or captions at different resolutions in this space. So this space has been flooded with attempts in 2015-16 time with a number of architectures which used convolutional neural networks and recurrent neural networks. Beyond that, then the next question is, like, if you have such images, can you interact with such images? Can you do the dialogues based on these images? Can you understand what is there in this image, and can you ask relevant questions and get the answers? Can you have continuous dialogue with them? A number of open tasks in this space came out, and what is a common sense knowledge, how that is represented, and how that can be extracted out of it. Another thread in this, which was parallelly happening, was generating images. One way to look at generation is a goal where you know that, okay, you're able to generate if your understanding is good. Well, that's one way to look at the generation. So in this case, the popular GANs, one way the images are generated with the help of a generative model from the scratch. And you have a discriminative network, which is basically asking the question, can I separate a fake or a artificially generated image from the natural image? There are two modules. The first module is generating an image, which is a trainable module, which is generating an image. The second one is trying to separate an artificially generated one from the naturally generated one. Now, so these two modules compete each other, and they play a game and learn to perform better over time and learn to generate images which are highly natural. So these are a few examples of images that are generated automatically. These are not realistic bedrooms. These are not real people whose faces are being shown, but they are generated automatically with a generative model. This generation also provides us mechanism for building networks, which has many other side roles in terms of building better representations, etc. So this is another example of such generation, where if you have a video, can you predict the next frame? Is it possible for you to predict the next frame and then see how that frame is? Like, this tells us our understanding of where the objects will move, what will happen in the next frame, and how that will have to be visualized in the pixel space itself. And also, like, if you are given more specific information, can you generate images which are more closer to the description or the information that is given as a prior information to it? So these are examples, like generating birds, which are of specific type, which are sitting in specific form, etc., are generated in this way. So we have control over the generation process in a much larger manner. And finally, in the space of image analysis, the low-level vision or a number of tasks has been formulated as an image-to-image transformation. And in this space was also changed a lot in the last year or last few years. So here are a few examples. How do you generate natural-looking images, like colorization? Or how do you convert an image into a new style or a new painting style automatically? Or how do you generate a high-resolution image? Or how do you create a 3D model from the 2D images directly? In many of these cases, our prior understanding of this, how this has to be done, is encoded into the neural network with the help of huge amount of data that it sees. So let me summarize. So the computer vision has been seeing a steady progress towards looking at harder and harder tasks. Moving from 2 class to tens of classes to thousands of classes to thousands of classes, and also providing structure to the output space in terms of the fine-grained representations of the classes. In the detection case, like face, the classical example of face detection that we all use on our mobile phones, to deformable objects and more complex objects, pixel level segmentations, finer understanding of the image into multiple labels and regions. Detections, bringing semantics by connecting to the language, nouns, verbs, and various semantic structures, interacting with the visual data, image-to-image translation, capability to synthesize. This is what the community is moving in the recent years. That's all. Thank you.
Thank you, Professor. We can probably take 1 or 2 quick questions since we're doing short talks. Yeah, there's a question here. I'll take this one first.
So you give a nice overview of the different techniques used in the computer vision over the past decade and in the past as well. But you talked primarily about the deep learning aspect as such. On a broader level, there are many works which actually were used in the computer vision community, specifically talking about pixel labeling. Probabilistic graphical models have been used a lot in the past. So what is your opinion on that, so there are some recent works which have tried to combine the two things, like the deep learning model followed by a probabilistic graphical model. So what is your opinion on that? Will it be totally data-driven, or the older techniques like the probabilistic graphical models have a role to play for better understanding, especially in the pixel labeling context?
I believe they have. I think the next years will see much larger connection between the classical machine learning with deep learning, or the popularly known as deep learning as a black box, the way many of us possibly complain. So I think the comment also originates from that. So I think there's a larger connection of the classical machine learning with the deep learning is going to happen soon.
We can take probably 1 more quick question there.
My question is about the text to image part,
Yeah.
the slide that you had shown. One part, in order to achieve that, one part is of course parsing and understanding the text, and then mapping it to the image. How is that done?
So this is
What are the elements? What are the basic elements on which you work to generate the image?
So this is presently being done with this called the GANs. It's a network which is able to generate images from scratch. Yeah.
Okay. Next. Okay. So maybe 1 more question, last one. Yeah.
Like human is solving simultaneously many problems. Like if I am visualizing the face, then face detection, emotion detection, then mood detection, as well as the beauty and ugliness of face. This means many kind of things at a time. So if I want to make CNN architecture, so different network we have to make for detecting these tasks. So how to combine these all networks?
I think there are a lot of research happening on multitask learning or more relevant things for that purpose. Maybe I think the machine learning session tomorrow will answer that, how CNNs can be trained for that purpose.
Okay, thank you.
Okay, so I think with that, we'll probably end this talk. Thank you, Professor Jawahar. As always,
you.
it's been a pleasure. Yeah.